Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at representing fractions and decimals in different bases. So let's look at our base 10 system. If we have a number like 0.3125, we know the column before the decimal point is the ones, because 10 to the power of 0 is 1. And then after the decimal point, we have tenths, hundredths, thousandths, and 10,000ths. So here we're using the rule that 1 over a to the b equals a to the negative b. So what that means is, say 10 to the power of negative 4 is 1 over 10 to the power of 4, which is 1 over 10,000, or the 10,000ths column. So it's important to note, if you raise a positive number to a negative power, like 10 to the negative 3, the answer is not negative, it's just very, very small. 10 to the power of negative 3 is 1 over 1,000. So let's look at representing this as a fraction in binary, which is base 2. So it's probably easiest to first represent this as a fraction in base 10. So how do we do that? Well, when you have a terminating decimal like this, just write the number without the decimal point as the numerator. The denominator is the lowest place value of 10. So in this case, the last column is the 10,000ths, so I'm going to put 10,000 on the bottom. So we can simplify this fraction. You might need the aid of a calculator. It turns out to be 5 over 16. So 0.3125 equals 5 over 16. So how am I going to write this as a fraction in binary? Well, of course, the number 5 in binary is just going to have a 1 in the ones column, no 2's, and a 4. So that's 5 in binary. And 16 in binary, it has no 1's, no 2's, no 4's, no 8's, 1/16. So this is a fraction in binary. 5 over 16 base 10 is this in binary. So how would I convert this to a decimal in binary? Well, decimals in binary, they have the same sort of structure here, but they're powers of 2 rather than powers of 10. So we still have the ones column before the decimal point. The first column will be halves, then we'll have fourths, quarters, eighths, sixteenths, and so on. So the problem here is we can only use the symbols 0 and 1 here. So I can't just put a 5 in the 16ths column. So what I'm going to need to do is I'm going to need to write this as powers of 2. Well, the decimal actually helps us. 5 is 1 plus no 2's plus 4. So I can write 5 over 16 as 4/16 plus 1/16. So that actually helps us because 4 over 16 I can simplify to a quarter. So now I've written this in a way that I can put it as a decimal really easily. So this number in binary, it would have no 1's, it's got no halves, 1/4, no 8ths, and 1/16. So the number 5 over 16, 0.3125, in binary is 0.0101. Again, we put this 2 there to show us we're in base 2. All right, what about going the other way? What about here if we have a number in binary and we want to convert it to a base 10 fraction? Well, this turns out to be a bit easier. So what we have here is we have 1 in the halves column, so we have a half. We have 1 in the quarters column. No 8ths, no 16ths, but 1 over 32. So we can simply add together this. We have 16 over 32 plus 8 over 32 plus 1 over 32, and that is 25 over 32 as a base 10 fraction. And if we want to convert that to a decimal, we can use short division, use our calculator, whatever it is. We have 0.5 plus 0.25 plus 0.03125, so that would be 0.78125 as a decimal in base 10. Okay, that's all well and good for what we saw as terminating decimals. What about for recurring decimals? So in order to understand recurring decimals in different bases, we're going to need to use the limiting geometric series formula. This is when you have heaps of terms, in fact, infinitely many terms added together. So if the sum is of the form a plus ar squared plus ar cubed and goes on forever, it turns out that this will not diverge. It won't just get bigger and bigger. It will reach a limit, which is a over 1 minus r. It will reach a limit if and only if r is between -1 and 1. So what do I mean by a and ar? Well, it just means you start with some random term and each subsequent term is being multiplied by the same number. This r is called the common ratio. So here, if I have this series here, 1 over 5 plus 1 over 20 and so on, the common ratio here is a quarter. So the reason the common ratio is a quarter, I'm multiplying each term by a quarter to get the next term. So a fifth times a quarter is 1 over 20. 1 over 20 times a quarter is 1 over 80. 1 over 80 times a quarter is 1 over 320, and so on. So because the common ratio, because the thing by which I'm multiplying each term is between -1 and 1, even if I add infinitely many of these terms, the sum just won't keep getting bigger and bigger. It will actually reach a limit. So that limit is a, which is the first term, divided by 1 minus r, which is the common ratio. It turns out that if you keep adding terms and terms of this series, then it will get closer and closer to the number 4 over 15. So the reason that it reaches a limit is because these terms are becoming pretty small pretty quickly. Eventually, these terms are going to be so close to 0, they're not really going to add anything to the overall sum. So how is this going to help us with a recurring decimal like 0.01 recurring in binary? So 0.01 recurring, we just repeat the zeros and ones over and over again. It keeps going forever. So what is this number in base 10? Well, we have none in the halves column. We have a 1 in the 1/4 column. So it is quarter, no eighths, a 16th. So we add that. Then there's 0 in the 1 over 32 column, and then there's a 1 in the 1 over 64 column, and so on. Here we have a limiting geometric series. Our first term is a quarter. The common ratio is also a quarter because we are multiplying each term by a quarter to get the next term. And that's because we're skipping one of the columns here. So this is half of the previous column. This is a quarter of that column. So we know that if we keep adding these forever, it will eventually reach a limit, and the limit will be a, the first term, divided by 1 minus whatever the common ratio is, in this case, a quarter. So you can put that on your calculator if you like. It's just 1/4 over 3/4, which is 1 over 3. So this in binary is 1 over 3 in base 10, which, as I'm sure you know, is 0.3 recurring in base 10. All right, let's now try to go the opposite way, which is rather more difficult. So we're going to write 0.2 in base 10 as a recurring decimal in binary. So 0.2 is a terminating decimal in base 10, but it turns out it won't be in binary. So how do I know that? Well, 0.2 is 1 over 5. So it turns out in base 2, the only fractions that you can write with a terminating decimal have a denominator that's a power of 2. You can't do that here because 5 is not a power of 2. It's just like in base 10, the only fractions that have a terminating decimal are ones whose denominator has only prime factors as 2 or 5. So we know this is going to be recurring because the denominator is not a power of 2. So how are we actually going to write it as a recurring decimal? So we're going to use the formula for the geometric series, a over 1 minus r. So in order to make this work, what we need to do is we actually need to write this as the sum of fractions whose denominator is 1 less than a power of 2. So 1 over 5, of course 5 is not 1 less than a power of 2, but 15 is. So we can actually write 1 over 5 as 3 over 15. And I want to write the 3 as the sum of powers of 2. So it's going to be 1 over 15 plus 2 over 15. Okay, let's now look at writing 1 over 15 as a recurring decimal in binary, and we're going to use that to get our final answer for 1 over 5. So for 1 over 15, what I'm aiming to do is I'm aiming to write it as a geometric series whose terms add up to 1 over 15. So in order that this works, in order that I can write it as a decimal in binary, I need each term to be a fraction whose denominator is a power of 2. So how am I going to do that? Well, let's start by choosing A. I need to choose the next smallest fraction whose denominator is a power of 2. I'm going to start with 1 over 16 because that is a little smaller than 1 over 15. So in my formula here, I'm going to change A to 1 over 16. So the idea behind writing 1 over 5 as the sum of fractions whose denominator is 1 less than a power of 2 means that I can find this value of r easily, make it a power of 2. 1 over 15, I can make this bottom into 15 over 16 like this. So this is 1 over 16 over 15 over 16, which equals 1 over 15. So 1 over 15 can be written as a geometric series with first term 1 over 16, common ratio 1 over 16. So the next one will be 1 over 256. And after that, timesing by 1 over 16, I get 1 over 4096 and so on. So 1 over 15 as a recurring decimal in binary, so there's nothing in the 2s, 4s, or 8s column. There is 16, 1 in the 1 over 16ths column, then 1 over 32, 1 over 64, 1 over 128, and then there's a 1 in the 256 column, and so on. We can see 1 over 15 will have a 1 in every fourth column. So that means that 2 over 15, we can just take our answer and times by 2. Now, timesing by 2 in binary is analogous to timesing by 10 in base 10. We just move the decimal point 1 spot to the right. So 1 over 5 is 1 over 15 plus 2 over 15. So we can just add together these two. So 0 plus 0 for the first couple of columns, and then the third one is 0 plus 1, and so on. 0, 0, like this. So what we can see is it's 0.0011, 0011, and so on. So in binary, 1 over 5 is going to be written like this as a recurring decimal. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.